One second.
High tech.
So,
wow.
Welcome everyone to this week. I can hear myself. Welcome everyone to this week's Applied and Computational Math seminar. It is my pleasure to introduce Cameron Hall, who's a lecturer in engineering mathematics at, well, he is in the Department of Engineering Mathematics at
mathematics department.
and as I just checked, Cameron is originally from Australia, where he did his undergrad. Then he was at Oxford. Then he was at Limerick, and now he's in Bristol. That's, yeah. Is that good enough?
That's a good description. Yeah, that's the gist of the trajectory.
Biography. Okay, and so it's over to Cameron, and I'll put my laptop next to him so that you can see him speak as well. And this is being recorded and will be put on our YouTube channel. So yeah, over to Cameron.
Cool. So I'm going to need to that looks like it works. Yep. So yes, I'm going to give you a talk on some stuff that I was doing. I have to always these days come with the caveat that this is some work that I was doing before the pandemic, because it is interesting to look at contagious processes on networks, and has in fact been delayed by the pandemic because we then got very, very busy just surviving, doing teaching, redoing all our teaching in new formats, then redoing all the teaching again in new formats after that. So I'm proud to say that at least part of this is now up on archive and has been submitted to a journal which I did not realize was quite as slow with even the first step of its reviewing process as all the other things. So it's submitted on the 24th of August, hasn't yet been sort of like desk rejected or sent out to review as we speak on the 9th of November, because that's the way things can be for some journals. But it's a nice little bit of work looking at models, trying to make efficient models of contagion dynamics on networks. And this is work with a PhD student of mine, Bram, at the University of Limerick. Bram was started a PhD with me, and then a few months later I disappeared off to Bristol and cruelly abandoned him. So he has not actually done as much on this sort of contagion on network stuff as on all sorts of other interesting things about dynamics on networks, in particular looking at pattern formation on structured networks and all sorts of interesting dynamical systems on networks. And he's now at the writing up stage at the end of everything. But what he and I were working on is looking at contagion dynamics on networks. So there are lots and lots of different ways of considering contagion, both in general and on networks. And we're going to concentrate on a very, very simple, the simplest contagion model, rather than complex contagion models where the effects of multiple neighbors sort of like multiply and affect with each other. Essentially, we're going to have a network, a graph, where each node represents an individual, and those individuals can be in a range of different states. So in a classic SIR model, each node is either going to be susceptible, infected, or recovered at any particular point in time. And then these nodes change their states over time. And this is going to be sort of like Markovian dynamics. So there's no history dependence on things, just the current state tells me about what changes are permissible from the existing situation. And the simple contagion in the sense that I just add up the number of infected neighbors that I have, and that gives me the total force of infection on me, the total rate at which I'm going to get infected myself. And we're interested in the dynamics of this system. We're interested probabilistically, what is the probability that a given node is in a given state, susceptible, infected, or recovered at a given time? Just that simple question, rather than looking for for critical thresholds of parameters or what the equilibrium is or things like that. We're going to be interested in the dynamical changes over time. I forgot to say at the very beginning, feel free to interrupt or anything like that at any point throughout the thing. There will hopefully also be plenty of time for questions at the end, but feel free just to jump in with something at earlier stages if you'd like. That's right. That is a good question. We're going to be considering a fixed network, but where the states are able to evolve over time. So yeah, I'm going to be using colors. There'll be a few little pictures and things like that throughout this. So in general, I'm going to have blue for my susceptibles, red for my infecteds, and yellow for my recovered/removed nodes. And for a simple SIR dynamics, if a susceptible node blue is connected to an infected node red, then at a given rate, the susceptible can become infected. And then an infected node that's just sort of like there floating in the pattern at a given rate can become recovered. And as a general setup for the system, we're going to say that those rates can be dependent on the specific nodes involved. So for the case of here, I have written lambda ij to indicate that this is the rate that is specific for node j infecting node I. And for gamma, the recovery, I've given a subscript k to say that's the rate at which node k recovers. In many cases, we're going to take these to be independent of edge and everything like that, but the theory works when it's all completely edge and node dependent and things like that. So where convenient, I'll present it in the more general format as well. So that's the nice little pictorial demonstration of what's going on. So the way in which where we started with all of this was we wanted to understand how this is affected by the topology of the network, particularly when the network has some sort of spatial structure. And by spatial structure, I mean essentially I could dot down the nodes in some sort of space, and then the distance between the nodes has a relationship with their probability of being connected. And what I wanted to see is some sort of idea of, okay, if we start an infection, then it should sort of like spread spatially through that space, and there should be some sort of like maybe a traveling wave approximation, a continuum approximation of what's happening with this discrete spreading through space. That was the original plan for this research. It turns out there's another question that needs to be answered before that, which is, what are the differential equations you should be solving even in the discrete problem before you try and take that discrete problem and turn it into a continuum problem. So I've got a few little videos, partly just to show off that you can have videos and things like that to start with, just to show off that difference between the between spreading processes in different types of network topologies. So here I just have a random graph where the average degree is about 4, and I've got 91 nodes, but they are equally as likely to have been connected to each other as any other. And if I look at the sort of a video of the spread of infection here, I find that very quickly the infection has gone through, and now I'm just in the process of a few things recovering in the last little stages. It hasn't quite got every node, but it was really quick in getting to everything. But if I have a spatial network, so here's an example of a spatial network on a lattice, same number of nodes, pretty much the same average degree and things like that, and look at what happens on a particular run through this. And it's the time scale is the same. It's taken a bit longer to get as far as it has, and it certainly hasn't been able to spread out to everything. It's a sort of a much slower growing process. And this is the same not just for very, very structured spatial networks, but for random spatial networks. So this is the type of random spatial network where essentially the probability, the log odds of a connection is a linear function of the distance between the two nodes. So I hopefully these ones were uniformly distributed throughout the space, and then the connections were made using that rule. So we saw, if we go right back to the start, we saw sort of like a bit of a wave starting to evolve out from the center. And if I had a much larger thing, then you can sort of like see much more of a structure to the growth of the process. And but again, it's a little bit slower than the initial Erdős-Renyi version, and even more slow is if I have a ring where each node is connected to its two nearest neighbors around this ring. And then it is not a very, very quick process, and it comes to a halt in this direction and is then just slowly moving its way around this side of the ring, so that by the time we reach the 15 time when we've stopped for all of the others, this has only got about halfway around. It's still live, it can still sort of like infect that node, but it's also much more limited in how far it can get. And the question is, could we do something where we can express these sorts of things as looking at, rather than a particular simulation, the probabilities on the basis of a large number of simulations? As I alluded to before, one of my backgrounds is in using asymptotics to go from discrete systems to continuum systems. We wanted to do all sorts of things like that. And there are some nice observations, like some people have done observations of what they call hop and spread dynamics, where you see a growing patch, and then because there'll be a long range connection, it'll seed a new patch that will start to spread somewhere else on these spatial networks. But that was for a very specific class of spatial networks. Can we do things like that more generally? And what we'd like to do is start with a system of ODEs. And with that whole prelude about discrete to continuum out of the way, the rest of the time, I'm just going to be talking about these ODEs and what should the ODEs actually be for describing the dynamics. So this slide again, just to remind us what we're talking about. Blue, red, gold for susceptible, infected, recovered. And we have different rate parameters for the rate of infection is going to be lambdas, and the rates of recovery are going to be our gammas. Now, let's describe the states of our different nodes. So the state of our ith node, we're going to write as being either S, I, or R, just to represent the state of that node at time t. And I'm going to use angle brackets to represent probabilities. So angle bracket around SI is the probability that the state of node I is S at that particular time. So angle brackets, things in angle brackets will always be functions of time. And these are essentially the things that we're going to want to solve for. We're going to want differential equations for angle bracket S, angle bracket I, and so on. And another little bit of notation, I'm going to use an N to represent the set of upstream neighbors. So the set of nodes that could infect me is my N, as N of me would be the set of nodes that can infect me. Now, with that sort of setup, it might seem like a neat set of differential equations that I could use to describe this would be this sort of things here. So the rate of change of me no longer being susceptible is to do with the sum over all of the neighbors who can infect me of the rate of infection times the probability that they're infected times the probability that I'm susceptible. And it all looks like it makes sense, and I could, that's a nice closed system of equations, and I could go and solve them, and the talk would be over. Unfortunately, this is just an approximation, and it's an approximation that goes by various names. I'm going to be mainly using the node-based mean field approximation as the long wordy name for it, but it goes by a lot of different names. And the reason why it's an approximation is that it implicitly assumes that the states of these neighboring nodes are independent of each other, that I can happily multiply the probability that my neighbor is infected by the probability that I'm susceptible and get a meaningful result out of that. But that's not the case. If my neighbor is infected, it's quite likely that they've spread the infection to me, or I spread the infection to them. So the joint probability of a node and their neighbor being infected is going to be greater than the product of those two nodes individually being infected. It's all of the node states are correlated with each other throughout the system. So that means that this is going to be just an approximation, and it's going to be an approximation in general that overestimates the rate of infection, because this product of the probability of being infected times the probability of susceptible is always going to be larger than the true joint probability that my neighbor is infected and I'm susceptible. So the correct formulation should be something like this, where instead of having those products of probabilities, I've written in angle brackets both of the things to represent that joint probability. And we would like to have a representation of this which is even better than the current version of things. We could then work out equations for those joint probabilities, but they would then be dependent on the triple probabilities. The triple probabilities dependent on the quadruple probabilities, and all of a sudden we've just ended up with the full-on master equations for everything again, and we've got 3 to the n equations where n is our number of nodes, and we're not happy about trying to solve that system of differential equations. At some point, we need to make some sort of a closure approximation. This is something I've already said, that in general, this product of those probabilities is always larger than the true joint probability. So the mean field approximation overestimates the speed of contagion. And so the idea that we would like to do, in order to, rather than use pair approximations, triple approximations, and the rest of it, is to find a realistic underestimate of this joint probability based on those node state probabilities, and then combine that with the overestimate from the first order of the node-based mean field approximation to give us a better hybrid node-based approximation, as well as noting that we now have upper and lower bounds on our rate of infection, rather than just it can't spread faster than this. Rather than just an upper bound, we could get upper and lower bounds, and we could combine them in some sort of way in order to get a model of the spread. So that's the overall idea of what we're going to talk about. So having spent my first sort of like 10, 15 minutes or whatever, just giving a general waffly overview, here is the overview of the rest of the talk. So rather than do all sorts of nice discrete continuum things like that, what we're going to do is we're going to start with an even simpler model. We're going to start with the SI model, and we're going to consider node-based estimates for this joint probability in an SI model, and find a lower bound on this IS probability and show that that bound is exact in certain cases. Then I'm going to go back to the SIR model and derive a node-based model which is exact in certain cases. So it's the same thing as before, but in the opposite direction. I'm going to derive a node-based model that's exact in certain cases, and I'm going to wave my hands vigorously and possibly endeavor to convince you that this is also a lower bound for the dynamics of IS in the general SIR case. And then finally going to introduce this hybrid node-based model of contagion and compare them for a few real cases sort of like structured networks, and look at dynamics on them. So that's the plan for the rest of this talk. So SI model. All of a sudden, all I have are 2 equations, though the only options are to be susceptible or infected. And the only thing that happens is I cease to be susceptible and become infected, and I do that at a rate which is proportional to the probability that I'm susceptible while my neighbor is infected. Once infected, always infected, and those are the only 2 possible 2 states. Last bit of notation that I'm going to use for this talk, and it's a very simple bit of notation. I'm going to use the power of plus to indicate the positive part of something. So it's going to be 0 if my input is negative, and it's going to be just x itself if x is positive. Now, I've got this lower bound on IS in this general thing. So every node is either susceptible or infected, and I'd like to convince you that this joint probability that my neighbor is infected while I am susceptible is greater than or equal to the positive part of subtracting their probability of being susceptible from my probability of being susceptible. Now, Some of you possibly just agree with this, and it's all sort of like obvious and natural already. I found this a little hard to get round my head. So I have a little picture, and if I were doing very, very nifty slidey animations, I would try and animate it and sort of explain what's going on here. So let's say here's my, for particular values of these probabilities, here's my probability of being susceptible and my probability of being infected. And here's my neighbor's probability of being infected and my probability of being susceptible. The smallest possible overlap I can get is by making these as big as possible, making the overlap area, the S overlapping with S and I overlapping with I as big as possible. If I stick this pie chart on the top of that pie chart and rotate things around in order to consider the different combinations of things together. So this smallest IS I achieve is by, I can see is the difference between my S probability, my S share of the pie, and the SJ share of the pie, because that will give me the largest possible SI, SJ together, where I'm just plonking this right over the top of this and then having a bit of extra bit, which is overlapping on the I side of J. I've said that in terrible words, but hopefully the pictures and my general hand waving is good enough to make that nice and clear. But the consequence of that is that this probability of my neighbor being infected while I'm susceptible is always greater than or equal to that difference, and because it also has to be greater than or equal to 0, I can have this positive part of that difference as well. Is that all good with people? Yep, I see lots of nods. I've probably labored that slightly too much. Okay, right. So that's we've agreed that this is a lower bound on what my joint probability IS is going to be. Now let's consider dynamics on a chain. So I've started at t is equal to 0. I've started with the node on the far left-hand side being infected, and everything else beyond that is susceptible. At all later times, I notice that essentially all of the infected nodes are on one side and all of the susceptible nodes are beyond them on the other side. So that tells me that if my neighbor to the left of me is susceptible, then I must be susceptible. And if my neighbor to the right of me is infected, that means that I'm in the infected bit of the chain. I must also be infected. So that's all neat, because what that tells me is that this probability of my neighbor who can infect me being infected while I am susceptible, that's this joint probability here. So that's the probability that I am susceptible minus the probability that we are both susceptible. And the probability that we are both susceptible is ultimately just going to be the probability that my neighbor is susceptible, because the only way that we are both susceptible is if my neighbor who could infect me is susceptible. So it just gives me this difference back again, the probability that I'm susceptible minus the probability that my neighbor who could have infected me is susceptible. So that looks suspiciously like this SI minus SJ with that positive part on there. In fact, if I considered my other neighbor, SI minus SI plus 1, that's always going to be negative. And so the positive part of that is going to be 0. So this I could use precisely throughout. In this dynamics on a chain situation, I can always say precisely that the probability that my neighbor is infected while I am susceptible is the positive part of the difference between our probabilities of being susceptible. So this works on a chain, and even more generally, this works whenever the network is a tree and there is a single source of infection, because you can see there's nothing special about the chain. I could have had branches, I could have started with it being able to go in more different directions. As long as the network was a tree and I've got a single infected node at t is equal to 0, it's always true that the probability of another node being infected while I'm susceptible is the positive part of our differences in our probabilities of being susceptible. And this is nice. This means that I now have a set of differential equations which is very, very closed. Very, very closed. It's closed. There's no very, very in it. This system here, the full dynamics, can be just written as dSdt equals minus the sum over my neighbors of the rate of infection and then the positive part of this difference. And I don't even need to worry about the i's or anything like that. I am just tracking the s's, and I've got a nice simple system of differential equations which I can solve with those initial conditions. Here is now where I'm going to very briefly wave my hands and say, it turns out we can do it thoroughly using some analysis of monotone dynamical systems, if that's something that anybody is into here. So using monotone dynamical systems, we can show that for any graph subject to any initial conditions, the solution to this problem here is always going to give me a lower bound on my probability of being susceptible. Yes, that's the right way around. Yeah, so I can. Sorry, I should have looked at the slide, and the slide would have told me what it is. It's an upper bound on my probability of being susceptible using this node-based tree approximation. So this is generally true for an SI approximation, and we're going to actually get something similar for SIR as well. Having done the SI thing, we'll go a little bit more speedily through SIR, but essentially, if I can set up the same sort of thing on a chain, and again, the trick that I notice is that on this chain, all of the infected and recovered nodes are on that left-hand side, and all of the susceptible nodes are on the right-hand side. So the probability that I am susceptible, given that my neighbor to the left is susceptible, is equal to 1. And I can go through, and I'm going to use that in a similar sort of way for an SIR model as well. So now I say the probability that my neighbor who could infect me is infectious while I'm susceptible is the total probability that I'm susceptible minus the probability that we're both susceptible minus the probability that they're recovered while I'm susceptible. Now this SS, I can do the same trick as before to say that that's their probability of being susceptible. And now the only nuisance is to work out this joint probability that they're recovered while I'm susceptible. But I can do a trick with that as well, because the only way for them to end up being recovered while I'm susceptible is for them to be the rightmost node and for them to recover. And then once that happens, that state is permanent. If there's no way that this can change in this chain system, there's no way the infection can come around the other way. The only way this gold-blue pattern can happen is if there was a red-blue pattern and then the red went gold. So this probability, the rate of change over time of this probability is just to do with the recovery rate of the infected in an IS infected susceptible pair. But we also have another differential equation that involves this. In addition to this, we know that the rate of change of being susceptible is also proportional to this IS pair. And so this drs dt is just proportional to ds dt for that neighbor, which was sorry, for me myself. Yeah, that's fine. Yeah, for me myself. So I can end up writing this RS pair by integrating up this differential equation and applying the initial conditions throughout. I can write this joint probability purely in terms of my probability of being susceptible. So that little trick there then means that I can even get rid of that RS term in my original problem. So I ultimately get that my joint probability of my neighbor being infected while I'm susceptible, I can purely write that in terms of my probability of being susceptible and their probability of being susceptible on this chain. So ultimately, in the SIR model, I have this nice, very, very simple model of which is exact on a tree with a single source of infection, exact on a chain and everything like that for the dynamics of the entire model. So also notice these are linear differential equations. It's not just that I've boiled it all down to a system of differential equations. These are linear differential equations. They're completely decoupled from I, even though for SIR, you'd think I have at least 2 differential equations I need to solve. All I need is the S equations solved. And they can be solved sequentially. So the probability of the the source of infection being susceptible is just 0 and remains 0 over all time. But S1 depends only on S0, S2 depends only on S1 and all the way through. So this actually has a simple closed form solution. So if I've got my lambdas and gammas being independent of the nodes, then I can just apply a D operator stuff, which I was taught at undergrad and have never used since. It was so nice to be able to use some D operator techniques, or you could use Laplace transforms or any other sort of method you like. And you could get a simple closed form solution for SIR dynamics on a tree or a chain or things like that. I mean, it's not particularly useful because when are you going to have contagion on something that just sort of like has a completely sequential tree pattern? But I've looked, I haven't found this anywhere. I'm sure this must be well known. It's just not well known to me. So if anybody can sort of like point to where I should have been referencing this from in the submitted paper, I'd love to know. But is that the answer? It's a what process with extinction? Cool. Well, when the rates vary, you don't get this nice sort of like simple answer, but you can still apply the same sort of thing and you just get a really, really horrible answer. I'll have to sort of like, and look that up because again, as I expected that this is the sort of thing that is well known. I am always moonlighting in another area of maths from my origin, and that's the way I like to play. But it means that I'm always, whenever I'm giving a talk, I'm always saying things in the knowledge that other people will know more stuff than me. But it would be nice to find out more about the details of that afterwards. They've got this idea of only connecting to your polygroup structure, essentially. It's very close to your SI problem. Yes, yes. But this okay, cool. I'll have more things to look up. So yes, exactly the same thing as I was saying before. If my underlying network is a tree and I've got these specific initial conditions where just one of the nodes is initially infected, then this is an exact solution of the problem. And again, via the magic of monotone dynamical systems, for if I've got any graph and I'm subject to initial conditions with no recovered nodes, it is possible to deal with initially recovered nodes, but it's just a bit of a mess mathematically to stick in. So if I just promise you there's no recovered nodes, then we can obtain an upper bound on S by solving this system here. So we now have our required system, which gives me an upper bound, which I want to combine with the node-based mean field approximation, which gives me a lower bound on the system. And so here are the two different approximations written out here. And essentially, the main idea is just to combine them with naively in the first instance, if we don't know what better to do, let's have a parameter alpha, which is somewhere between 0 and 1, and say that my rate of change of my S over time is alpha times one model plus 1 minus alpha times the other, and see what that does. So alpha equals 0 in this particular case will give me the tree-based model. Alpha equals 1 is going to give me the hybrid, is going to give me the node-based mean field model, and alpha anywhere in between I'll call a hybrid model. Hypothetically, alpha could depend on the individual nodes. It could depend on time, all sorts of things like that. But for the most part, we'll talk about what happens when you take alpha to be a constant. I suspect that my alpha should be decaying towards 0 over time because it doesn't capture it has some problems with capturing the long time behavior, which could be fixed by making alpha go to 0 over time. But that's a fine detail. So we then have the issue of how do we choose this alpha? Lots of things. The main thing we've stuck with is let's take it to be a half in the absence of any better information and see how that does. Also looked at using some early time asymptotics to get some information. Fortunately, that said alpha should be about a half when we did a 4 ring because that's the best thing that I could do. But also we've done a little bit of things with using essentially some Bayesian inference to run some simulations and use those simulations as being the experiments that can inform what the alpha posterior could look like, and using enough information to ultimately get it down to something reasonably tight for different types of networks. So those are the sorts of things we've played with, but open to suggestions. If you can think of good ways of picking good alphas, that's also. Yeah, so I'll talk about that a little bit later, but different networks gave different optimal alphas and different sort of like ranges of alphas. So sometimes it was very sensitive to alpha and sometimes it wasn't very sensitive to alpha at all. But for a lot of typical, and I haven't presented it here today, but we've also done some things on some real contact networks. There's the Dublin contact network from 2015 or something like that, where they got people to wear RFIDs and see how they ran into each other and things like that. For things like that, the optimal alpha came out as about 0.4 or something like that. So about a half doesn't seem to be completely crazy in these sorts of cases. Wait, so we're going to show a bunch of pictures which will include how bad are the bounds. So for all of these, there's a single initially infected nodes. I'm keeping my lambdas and gammas the same. Alpha equals 0.5 whenever there's a hybrid model. The true results are the basis of 10 to the 5 Gillespie simulations that have been averaged. That's just the terms and conditions of the graphs that follow. But starting off with a tree, just because for a tree, we expect the tree-based approximation to be very, very good. Sure enough, it is. But notice that there is even now a big difference between the tree-based approximation and the node-based mean field approximation. We've also got the pair approximation in there, which I haven't talked about. The pair approximation is also exact on trees, but is computationally more expensive than these node-based approximations because the number of equations that you have is twice the number of nodes plus 3 times the number of edges, whereas the other thing we just have is twice the number of nodes as the number of differential equations that we're trying to solve. And that doesn't sound like it's a huge difference, but on a large network, it really starts to slow things down for solving these ordinary differential equations. So, sorry, I should have pointed out. Yes, and this is an issue that crops up with the node-based mean field approximation all the time, because it doesn't remember where the infection has passed from. So if it says you have a low probability of being susceptible, but there is a probability that your neighbor is infected or something like that, then that will inform more infection of you, even though possibly the only way that you'd still be susceptible at that stage is if your neighbor had recovered or there was no way of the infection spreading around to you. So those small probabilities of being infected always end up pushing down it's not technically quite 0, but it's always basically 0 as the T is infinity probability of being susceptible. And that's why I think alpha should tend to 0 in the long run, by the way. And this is the same as the tree model, just with the probabilities of being infected rather than the probabilities of being susceptible. But this is what happens for a random graph. So here, just complete random graph, average degree 10. Notice the difference, the distance between the tree-based approximation and the node-based mean field approximation. So yes, the tree-based approximation does give me an upper bound on S. It's not a very tight bound on S. If I look at the black line as being the true solution, there is a huge gap between my upper and lower bounds provided by the node-based mean field approximation and the tree-based approximation. But at the same time, the hybrid approximation, taking the alpha to be 0.5, is not as good as the pair approximation, but is a lot closer in this particular case. And for random graphs, the optimal alpha often would push up closer to 1. It would be more like the mean field approximation than it is like the tree approximation, just because in a random graph, everything is randomly connected to everything else. It doesn't have that same sort of level of structure of the tree-based approximation. So in essence, the nodes feel the mean field as a more appropriate approximation. And we can see the same for the infected case. By the way, it's worth noting that this whole argument to do with the bounds only applies to S. It doesn't apply to I or to any of the others. So I know that my probability of being susceptible has got to be between the blue curve and the sort of like teal curve, but there's no guarantee that the infected the true solution is between the blue curve and the teal curve or anything like that. 5 nearest neighbor ring. This one I find really interesting. I want to know why it's so linear and what the slope of that line is, and whether I can use I can find an alpha that gives me the correct slope of this line. All of the approximations give me very, very linear sorts of traveling wave looking solutions. I don't quite know why. It's intuitively it makes sense that you would get some sort of like traveling wave dynamics in the spreading probability, but I don't know why it's as linear as it looks to be, and what controls things in different cases. I thought people were about to tell me, but no, that's this. So I've got a ring, and if I'm here, then I'm connected. If I'm I'm connected to I minus 1, I minus 2, I minus 3, I minus 4, I minus 5, I plus 1, I plus 2, I plus 3, I plus 4, I plus 5. Yeah, and that's why I'm comparing this with the any that we saw before had average degree 10, and then this one, every node has precisely degree 10. I have 5 minutes left. That is fine, because I'm essentially just showing pretty pictures, and then I'll have some conclusions at the end. And here's what the probabilities of being infected look like. I also don't know why the hybrid model and the pair approximation are so close in this particular case. I even double checked to make sure I wasn't using the same data file twice, and was just, they are genuinely different curves, and you can see that they're not quite entirely over the top of each other, but they're very, very close, and I don't know why. Lots of things to like figure out. And now we can start with something like this 5 nearest neighbor ring, and we can randomly sort of like cut and rewire some of those connections to get a Watt-Strogatz network. And in this case, with a small amount of rewiring, I have picked this amount of rewiring so that the optimal alpha is about 0.5. It's not quite exactly 0.5, but in this particular case, by slightly cheating, the hybrid model does really, really very, very nicely, even better than the pair approximation. But notice it doesn't capture the tail behavior very well. None of these do. None of them really capture the fact that there's an appreciable probability of nodes remaining susceptible at long times. And that's why I think alpha should vary dynamically with time. Same sort of thing there. Same sort of thing, lattice, briefly. Again, they match very nicely as well. Again, hybrid and pair approximation, apart from the fact that hybrid is a lot quicker to compute, you can't really tell the difference between them in the dynamics. A little bit of a gap between them, but not very much. Don't know why. Again, don't know why they match so well with each other, but notice that they are both better than the mean field approximation, and the tree approximation is just terrible. And so, yeah, even at this sort of state here, there are plenty of open-ended questions, including what I sort of said before, of like, why does the hybrid approximation really nicely match the pair approximation in certain cases? Is there a way of extending the analysis for SIS or SIRS models and things like that? Because the whole argument that I gave about what happens on trees, it completely falls over as soon as it's possible for a recovered node to become susceptible again, because it relied on this whole idea that the RS state is permanent and can only be achieved one way. If I've got my R's becoming S's again, then all of a sudden that's no longer going to be true. Are there other node-based models that would be good ingredients? I have alpha of one and 1 minus alpha of another. Are there other node-based models that could be ingredients in there? So I've got a weighted average of multiple things that add up to 1. As I was pointing out, what is the best choice of alpha? How does it depend on network parameters? How do we correct for the right long time behavior? And how do we obtain, as I said, these nice linear things? There's what's the correct wave speed? There is some stuff by Tim Rogers, and I've forgotten the first name of more, but yeah, people in Bath have been doing some things which might be related, but I don't understand what they've done well enough in order to make a clear comparison. And there's further work. This can actually be extended to SEE with arbitrarily many exposed states in between IR analysis. So this and the SIR analysis for the tree-based model, not the hybrid model, but just introducing all the heavy maths for the tree-based model, is in something which is actually written up on archive, hopefully being reviewed sometime soon. And it's, again, it works exact on trees with a single source of infection, even with arbitrarily many exposed states in there as well. It's just quite messy maths. And I'd like to explore a bit more how this relates to message passing models, which are another technique that gets used in some of these sorts of areas, and with the other things that I'm just learning about now. But in conclusion, it is possible to construct this node-based formulation of SIR dynamics that is exact on trees with a single source of infection, which is kind of boring, because when are you ever going to be looking at contagion on a tree with a single source of infection? But it's mathematically nice, and we're mathematicians. We're allowed to like things that are mathematically nice and everything. But the nice thing is that this tree-based model does give us a bound, a very, very loose bound, but still a bound, which is a nice thing. And that justifies the idea of combining it with the mean field, the node-based mean field model, which is a bound in the other direction to give us some sort of average dynamics. This then gives us a new hybrid approximation, which is comparable in performance in terms of matching the true dynamics to the pair-based approximation. Sometimes terms and conditions apply. But there's plenty of further analysis to do in order to hone it better and understand how and why it works and in what situations it works well. But yeah, here's a nice little idea and some exploration of it so far. Thank you very much for having me.
Very interesting talk. I think we have time for 1 or 2 questions, and then we have to leave. So if anyone has any questions, please ask us away. That applies to people on Zoom as well.
Ooh. Okay. Yeah. So what would again, just be patient with me being ignorant. What would non-extinction be in this situation? Because ultimately everything is either recovered or susceptible in the long run. The infection has hit absolutely everybody. But everyone is recovered at equilibrium. Okay. Yeah, that's it. That's interesting because that gives me a. Let me think. So, is there any reason? Because fundamentally, all of the differential equations are constructed on S, or ultimately in the tree-based model, not in the hybrid approximation, but just starting with the tree-based model, everything are differential equations on S as such. I'm trying to think whether there are things that stop me from going backwards in time on the differential equations from a recovered state. Clearly, a recovered state could have just always been there. So it's a little bit tricky to resolve. Oh yes, and I need, in order for my things to work, I need everything to be initially susceptible or infected. That was in order to go forwards in time. I haven't thought about essentially trying to think of a problem where, in order to impose some sort of condition on the final state, I am trying to run things backwards in time. But I think that it should be possible to do something, because, like, if we look at the closed form solution and things like that, you can read off from this closed form solution what the S is at equilibrium and things like that, because these are all, this is the term that's going to zero. So I have 1 minus lambda to the I over lambda plus gamma to the I as my S at equilibrium. I'm just trying to think of how I deal with trajectories where I'm essentially just wanting to select those which don't go to this steady state. I feel that because at equilibrium, I know that if this was susceptible at equilibrium, then everything beyond it is also susceptible at equilibrium, because again of those conditions, that I can essentially selectively remove all of those cases. I would need to sit down and think. There probably isn't an easy answer, but I feel like I can say more than nothing if I thought about it very, very carefully. It could be that I think about it very, very carefully and realize that I can't say anything, or certainly not anything interesting. But it feels like, because of the special structure of the equilibrium in the tree-based and chain-based cases, it feels like it should be possible to say more than nothing, but I shouldn't promise that.
Okay, any other quick questions? If not, then we can continue. So let's thank Cameron.
Thanks for having me. This is my first in-person seminar that I've given of the not quite after times. Yes.
Yeah, so this concludes the seminar. Thank you.